Okay, so we would like to talk about isolated singularities. So in this case, we think that we have a function which is defined on a disk with the exception of the center. So it's a set that looks like this. And the reason that we put a greater than 0 means that the center is not contained in our considerations. So imagine that you have a function which is analytic on a set like this. It turns out, and that's a fact, that it has an expansion into a series that consists not only of the usual terms that we've seen in case of differentiable functions, but also includes monomials with negative exponents. It's a Lorentz series, as we call such a series. So it's double-edged, if you like. And depending on the form of this series, which is actually unique, we have three types of possibilities. The first possibility is what is known as a removable singularity. And in the case of a removable singularity, it's as if we had actually used a formula that was problematic at the specific point, but the truth is that it could be remedied and the function could be extended to that point so that it's still analytic. So a good example would be sine z over z, or just an example, I'm not sure how good this is, but the bottom line is that sine z over z would be such a function that initially it's not defined at 0, but then we realize that it can be defined and it can be actually assigned the value 1. Then we have the case of what is known as a pole. So in the case of a pole, we always look at the negative part, if you like. That's the problematic part. So there is certainly a non-zero term in the negative part, and past that, on the left of that, everything is 0. So I'm giving this very, very simple example here, where you see I have a term of degree -2, then -1, and then all the good part. And this would be a pole of order 2. In the case that we're mostly interested in the case of the zeta function, we only have one isolated singularity at s equals 1. And this means that the zeta function has an expansion around that looks like this. It turns out that the coefficient that we have is 1. And it's a simple pole. It's what is known as a simple pole. So a pole of order 1 is also known as a simple pole. And it turns out that zeta of s minus 1 over s minus 1 is actually what we call an entire function, meaning an analytic function on all of C. And we would like to also mention one last case of a singularity, which we are not going to really encounter much in our study, the so-called essential singularity. And in the case of an essential singularity, what we have is a pretty wild situation. So C negative k is different from 0 for infinitely many k's. And the simplest example that we can give here is compose the function e to the z, which is otherwise a very nice function, with 1 over z. If we do so, we get a function that looks like this. It's 1 over 1 over z plus 1 over 2 factorial times z squared plus 1 over 3 factorial z cubed plus 1 over 4 factorial z to the fourth, and it keeps going. Okay, you pretty much take the expansion of the exponential function and you replace z by 1 over z. It turns out that such functions are very, very strange around the singularity. So there is a very interesting theorem that tells us that the set of values of such a function, no matter how close you come to the singularity, is very large. It's pretty much the whole set of complex numbers with one possible exception. If you juxtapose this with the other two cases, so in the case of the essential of the removable singularity, the limit actually exists. So the set of values very close to the singularity is going to be a little disk. In the case of a pole, very close to the singularity, what you're going to get is the complement of a disk, because the limit is infinity and the radius will become larger and larger as you approach the singularity. So basically what we're saying is that in the case of the essential singularity, what you get is the whole complex plane with the possible exception of one value. We're not going to look at essential singularities in any essential way in our study, and we're going to pretty much look at functions that are either analytic or have poles. And that's all. Thanks for watching.